All right, I'm going to explain Newton's three laws, but more specifically, I'm going to talk about common problems or questions that are asked on not only the AP exam, but also just physics tests in general. Some of these problems are tricky or things that you guys have asked me about in the past, and so I want to make sure that I really kind of cover these things each step by step. So let's just start with the first law. So Newton's first law. For the sake of time, I'll just write it out. So, this one is an object in motion, tends to stay in motion. An object at rest an object at rest tends to stay at rest and this is the most important part, unless acted upon by an unbalanced force. So Newton's first law is basically describing what we know as inertia. And inertia is the resistance to a change in motion. So an object in motion tends to stay in motion. That's a resistance to change, right? Or an object at rest tends to stay at rest. Again, a resistance to change unless acted upon by an unbalanced force. If I could condense this and make this easier to understand, basically, I would just say an object only accelerates when there's an unbalanced force. So what that means is, if you have an object that is not accelerating, there is no unbalanced force. So let me give you a few examples of all of these things. So this is still Newton's first law, N1L. And some examples are just like box on a ramp or on a table, flat table. We have gravity, normal, right? And this thing is at rest, so it's not accelerating, right? Let's real quick talk about acceleration, because if you don't understand what acceleration is, you're not going to get this law. You need to understand that. Acceleration is a change in motion. So if we are at rest, in order for us to become moving, we have to accelerate. So this box is at rest, it's remaining at rest, so therefore it is not accelerating. Let's look at another example. This one is super common, and I brought it up in class a couple times, but some people still hold on to it. Let's say we have a hockey puck, and it's moving across the ice at constant velocity. If I were to draw a force diagram for this, I would put gravity in normal. And a lot of students want to put an applied force going to the right because it's moving to the right. We need some sort of force that's pushing it to the right. But here's the most important thing, the main thing from Newton's first law is that an object in motion tends to stay in motion. A hockey puck sliding across frictionless ice will slide across frictionless ice forever. Forever and ever and ever, unless there's an unbalanced force acting on it. So if it encounters friction, if it bounces off of a wall, if a stick hits it, if it runs into an ice skate, all of those things are going to produce unbalanced forces. But if there was an infinitely long ice rink and we just hit a hockey puck and ice was assumed to be just frictionless, it would move forever down that ice rink, forever and ever and ever. And it would not need a force to push it to keep it going. All right? And that's super, super important. So this red force does not exist. You do not need a force keeping it moving. It is it is not accelerating, right? Because constant velocity means that it's not accelerating, right? There's two main ways that you know something's accelerating, or it's either, well, three actually. It's either speeding up, slowing down, or changing direction. We're going to talk about that soon in our next unit, actually. But that's how you know that it's accelerating. So if it's not doing any of those things, if it's not speeding up, slowing down, or changing direction, then if it's not doing those things, then it must be in what we call equilibrium, which means that the forces are balanced. So, an ice skater that's skating on the ice rink. Here's the ice rink, and they're moving at constant velocity. Is there a force pushing this ice skater to the right? No. And here's the other thing that I try to tell my students to hopefully help them remember that. Whenever you put an applied force on something, you have to ask yourself what object at that moment is applying the force on that person. If there's a hockey puck sliding across the ice, moving at constant speed, what object is pushing it? You might say, oh, well, you know, in the past, somebody had to hit it to make it move. That's true, but we're not talking about the past. We're talking about right now. Is there an applied force on it right now? No. And forces don't last into after they hit. Like, you can't apply a force on something and then that force just stays on that object. The only time a force is on an object is when you're pushing on it. All right? So that is Newton's first law. Some common problems is they like to ask you questions like this one. They also like to ask too, like if you throw an object up into the air, at the top of its trajectory, it's at rest for a moment, right? But it's only at rest for a moment. It's still accelerating. So be careful with that because that's kind of tricky. So if there's an object that's in free fall, it's always going to be accelerating with negative 9.8 meters per second squared. So just keep track of that. But in general, that's what Newton's first law means. So an object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an unbalanced force. And in fact, if I have a little bit of time, maybe I'll just make this just about Newton's first law. Let me show you real quick a simulation that really kind of hits home what they're talking about. If you go to forces in motion, there it is, forces in motion basics, and we play this. I like showing, we'll just do the friction one. So I'm going to turn friction off, and I'll just check all these things so you can see them. If I have this guy push on this box, this object is moving with a speed of 14 meters per second, and it's just sliding. The sum of the forces is 0. You see that? And it's not moving at all. Sorry, it is moving, but it's moving at a constant speed, and it's not accelerating. If I want to slow it down, I apply a force backwards on it. You can see the speed is changing, slowing down, but now we're speeding back up. And then once I stop pushing on it, the force disappears. You see that? Push, 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 stop. Now it disappears. So, and that's when there's no friction. The other thing that the reason why we have a hard time with this, and it makes sense, so you shouldn't beat yourself up about it, but the reason why we have a hard time understanding this is because on Earth there's always friction. So this little simulation right here where it says friction none, that's not very realistic. Everything that you can think of, including ice, has friction. So, you know, solving a problem where there's no friction is kind of confusing if you're thinking about your everyday life. So let's turn on the friction, and if I push on something, let me turn these guys on. If I push on something, you can see that it will accelerate, but when I stop pushing on it, it stops moving. It slows down until eventually it stops. And that is our experience on Earth, right? If we include like lots of friction, let's say I push on a desk, right? And I make it move and then I stop pushing on it, it just slides like that and stops. That's real life. But the reason why it stops isn't because we need to keep pushing on something to make it move. The reason why it stops is because there is an unbalanced force on it, right? Newton's first law where it says, unless acted upon by an unbalanced force, the unbalanced force is friction. See? I push on it and it stops because friction is unbalanced. It's slowing it down, it's accelerating it until now it's at rest and now there's no friction and now it's done. So, an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted upon by an unbalanced force.